chapter 2. Today, the quote for this chapter is from John Dalton. We mentioned him in chapter 1. These observations have tacitly led to the conclusion, which seems universally adopted, that all bodies of a sensible magnitude are constituted of a vast number of extremely small particles or atoms of matter. And he's the guy that came up with the atomic theory, which basically says all of matter is made up of little tiny particles called atoms. And that was a really big breakthrough. So here's a kind of a thought experiment. You take a piece of graphite, so you get your pencil and the tip breaks off, right? Take that little piece of graphite that broke off, cut it in half. Take one of the halves, cut that in half, and keep going. How far could you cut it in half? Could you cut it in half infinitely, assuming you had a small enough knife? Or would you get down to a point where you could no longer divide it? So that was a question that couldn't be answered for a very long time. But now we know that eventually you would get down to individual carbon atoms. And you can't cut a carbon atom in half. The word atom comes from the Greek word atomos, meaning indivisible. You can't divide an atom into smaller pieces and still have that element. Atoms compose all ordinary matter. In order to understand matter, we have to understand atoms. Atoms are a lot like Lego blocks, except they're round. In 1827, Robert Brown was looking through a microscope at some water-suspended particles that had come from pollen grains. And this is a video similar to what he saw, except without the ads. This is a better ad than the shirtless guy when I checked it earlier. So these are the particles he's talking about. And you see how they're jiggling and wiggling? Nice 28-second video. So why are they moving? Are they alive? What's going on there? So these are the sorts of questions, that we have when we observe nature. So initially he thought maybe the particles are alive, but he finally figured out that the source of that motion must come from something outside the particles themselves. So something's like hitting them or bumping them, pushing them around. A little while later, 1905, Albert Einstein. By the way, I'm going to mention these people's names and the dates and stuff. I'm not quizzing you on chemical history. Okay, so don't worry about that. He came up with a theory that explained what was known as Brownian motion after Robert Brown, who described this. So that motion of those particles is a result of the molecules of water bombarding those particles. So the water has thermal energy, which means that the particles in the water are moving. And so they're moving around and they're hitting those pollen molecules or particles. We can't see, the water molecules are too small, but those little tiny bits of dust we can see. So the pollen's getting battered and it causes them to move. So it's a little bit like throwing a beach ball out into a big crowd, right? And people hit the ball and it goes all over the place. And maybe the beach balls glow in the dark and all the lights are off and you can't see why this beach ball is moving around this stadium, right? It's just moving. But you can't see the people hitting it. So that's the idea here, is the water molecules are hitting the pollen and causing it to move. So the existence of atoms was inferred by this Brownian motion. There must be particles that are hitting these larger molecules. Sorry. I think my brain melted on the way to work today. There must be particles, like molecules, that are hitting those pollen grains and causing them to Um, Jean Perrin conducted some experimental measurements that confirmed Einstein's theory, and at that point all doubt was removed about the particulate nature of matter. So that happened in the early 1900s. In the late 1980s, a couple of guys at IBM were working on some stuff that led to the development of what's called the scanning tunneling microscope. And here's the main idea. You've got this probe that's controlled by a computer, and at the very tip of this is a little tiny needle. And so here we've zoomed in so far that we can see the atoms, and so at the end of this is one atom. And they're going to apply a voltage between this probe and the surface that you're studying, and the computer adjusts the distance of the probe from this surface so that the current that flows between them over this little tiny gap of space is constant. And so by moving this probe back and forth and the computer adjusting it so that it's a fixed distance from the surface, we can sort of feel the surface of almost anything. So that allows us to get some rather crude images of atoms. These are the Japanese kanji characters for atom, and the little red things here are iron atoms on a blue background of copper atoms. And so these are about the best pictures we can get of atoms. They look like little cones or something. We know that they're spherical, but it's an artifact of our crude measurement of them. And this is an interesting little video. I hope it still works. Okay.
So what we do to move atoms is a variation of what we do to see the atoms in the first place. So we can't use light to see them. So we're not looking through a microscope like the conventional microscope we used to. We need something that can see much smaller things than that. So what we do is take a sharp metal needle and bring it close to the atoms. And in a sense, we're feeling the shape of the atoms. So if you imagine that we have a surface that we're putting an atom on, we put it on the surface and so it holds still. What we do is take this metal needle close to the atom and sense its presence by measuring an electric current that flows. And as the tip of this needle approaches the atom, it sees more electric current, and we draw it up and over the atom to keep that current constant. So in a sense, we're feeling the shape of this atom. Then in order to move atoms, we observe that we have a sharp metal needle near it. We can bump into it by accident. What we can do is, instead of doing it by accident, do it under control. If this is our atom on a surface, we can move the tip close and we start to form a chemical bond between the tip and the atom. That chemical bond forms between most atoms. They like to bond to each other in most cases. So we start to form a bond such that the atom follows the tip around on the surface. We can drag it to a new spot. When we withdraw the tip, it holds still because the surface is holding it in place. And we can take an image and see where we've placed this atom. So that process, repeated over and over, is how we've built most of the structures in our lab. That's our bread and butter basic technique for moving atoms around.
So that was a big discovery. Makes it possible, sorry about that, makes it possible to make extremely small computer chips, right? Because if you need a little conductive wire, you don't have to take a small wire and somehow attach it at both ends. You can actually move copper atoms on the surface and maybe have a wire that's just like, 5 atoms wide or something. And so you can have really, really tiny things. Or, scientists do have fun. It's just kind of weird fun. So this is the world's smallest movie. So that's like those atoms there, that's like the ultimate small pixel, right? It's like you can't get any smaller than one atom. So if you take any digital image and you zoom in far enough, you see these little squares, right? Those are called pixels. So this is going to the ultimately small and making a movie using individual atoms as pixels. You know, is there any like benefit to society from making that movie? Probably not, but it's kind of cool. Anybody have any questions about that?
Yeah, that discovery kind of like, is this like really new technology that's recent?
So the scanning tunneling microscopy is from the 1980s. Yeah. So depending on your point of view, that's pretty recent. This one I was in high school, so it doesn't seem that long ago to me, but that was a long time ago. But it's not like the 1400s,
No, yeah.
right? Yeah. So it's relatively new. Anybody else? So just to give you an idea of how small atoms are. So the Library of Congress, there are about 35 million books there. And that takes up 840 miles of shelving. So imagine a road with, like a bookshelf, 840 miles long of books stacked vertically, not laying down, vertically. That's a lot of books. Imagine how many words are in all of those books, right? If you took all of the letters in all of those books and wrote them using letters the size of those kanji characters on the previous slide, just a few atoms tall, all the words would fit into an area of 5 square millimeters. So millimeter, half a millimeter is about that big. That's a lot of atoms, right? So atoms, mind-bogglingly small, but they are the key to connecting the macroscopic world that we can see with the microscopic and submicroscopic worlds that we cannot see. So an atom is the smallest identifiable unit of an element. There are 91 different naturally occurring elements and over 20 synthetic elements. Those are elements that are not found in nature but have been created in a laboratory.